So let's begin, friends. Today we are going to solve the numerical by relative velocity and acceleration method. This is the numerical of single slider crank mechanism. The crank of slider crank mechanism rotates clockwise at a constant speed 300 rpm. The crank is 150 mm and the connecting rod is 600 mm long. You have to determine the linear velocity and acceleration of midpoint of the connecting rod. This is the midpoint of on the connecting rod AB. Also, you have to find out the angular velocity and angular acceleration of connecting rod. So, after having this problem, you have to draw the space diagram. To draw the space diagram, you have to select one scale. So, we have selected appropriate scale of 1 centimeter equal to 100 mm. By using this scale, we have first drawn a horizontal line. Then we have located the O point, which is the fixed one. We have measured the angle of 45 degree in the clockwise direction. Drawn this line AOA of 150 mm with the scale of 1 centimeter equal to 100 mm. Then taking the distance AB equal to 600 mm. By scale it is 6 centimeter. Keeping the compass at A, cut this horizontal line. We got the B point. Join this A with the B. At B you are having the slider. In this way you have to complete the space diagram. So space diagram is drawn here. This is the space diagram by using some scale. We have marked the M point, which is the midpoint of the connecting rod AB, that is located at exactly at midpoint at 300 mm by scale. So after that, to start the velocity polygon, you must know the direction of rotation of crank. In this case, it is rotating in clockwise direction as given, and the magnitude of velocity of crank must be known. So as the speed of the crank is given, that is 300 mm, we have calculated the omega of crank AO. By using the 2 pi n divided by 60, we got that omega of crank OA is 31.41 radian per second. By knowing the omega, we have calculated the velocity of crank, that is omega multiplied by length OA, and that is equal to 4.71 meter per second. So we know the magnitude of crank. Also, the direction is known to you for the crank. For crank, you know magnitude as well as direction. So now it is, you can start with the velocity polygon once you know the magnitude and direction. To draw the velocity polygon, you have to select the velocity polygon scale. By knowing the values of crank velocity, that is 4.71, we have selected our scale of velocity polygon 1 centimeter equal to 1 meter per second, as it is shown here. Now, where to begin? Always to draw the velocity polygon, you have to start with locating the pole. Poles are the fixed positions from your space diagram. Which is the fixed position? O is the fixed position. So locate the pole first. So here comes the O. We have located the O pole in the space of your paper at appropriate location. So O is located. Now for the link OA, we are knowing the direction of rotation. It is rotating in clockwise direction, and the velocity vector for OA is perpendicular line. This perpendicular line you have to draw in the vector polygon. From where? If you have to draw the velocity vector for link OA, the velocity vector will be perpendicular line, but you have to, one point of the OA must be available. Either O or A must be available here. So we are having the O. Means you have to draw a perpendicular line to OA in a direction of rotation, that is in this direction from O. So it comes here. So this is the velocity vector for the OA link. Of what length? The length of it is 4.71 by using the velocity polygon scale. Then the link AB is there. Link AB velocity vector will be a perpendicular line to AB. But this perpendicular line you have to draw in the velocity vector diagram. How it is drawn? If you have to draw the velocity vector for AB, which is the perpendicular line, either A or B point should be available already. So which is available? A point is available. Means you have to draw a perpendicular to AB from the A point. So here it comes. This is the perpendicular to AB, which is drawn from the A point from here. And this is your velocity of B with respect to A. So after completing the velocity vector of BA link or AB link, next link is a slider B. Now velocity vector for slider B is a line drawn parallel with the line of torque. How the line of torque of slider? It is the horizontal. So the velocity vector for slider is drawn from the pole. Always it comes from the pole. So O is the pole. Draw a horizontal line to show the velocity vector of slider B. So here it comes. This is the velocity of the slider B. Now this horizontal line cuts the previous vector velocity of BA at a point B. So B point will get located here. So after locating this, you are having a M point, midpoint of the crank connecting rod AB. Now for AB, you are having vector AB here. On the same vector, you have to locate the M point. How to locate the M point on the vector AB? Because M point appears here on AB link. So M point on vector diagram should be on AB vector only. So how to locate this M point? To locate the M point on the AB vector, you have to use the ratio. That AM, small am divided by small ab equal to capital AM divided by capital AB. Now this, you will get the AM here. By using this capital AM, capital AB, which are known, small ab, you have to measure this distance. Directly keep the same distance here, you will get the small am. So after calculation, you will get that small am here. That is 1.5. 7 centimeter. So we have located the M point at from A, it is 1.7 centimeter from A. So we located M. Join the O with the M. After joining O with the M, we'll get the velocity of M point. How to calculate this? To find out the velocity of M point, you have to measure the OM, multiply with the velocity scale, that is 1 meter per second. You will get the velocity of M point 3.9 meter per second. To find the angular velocity of connecting rod AB, you have to use your basic equation, velocity equal to omega multiplied by r. Apply this equation, velocity of AB equal to omega AB multiplied by radius AB. Using this, we have calculated the omega. So to omega AB will be linear velocity of AB divided by AB. How to find out velocity AB? Velocity AB is measure the vector AB from the velocity diagram multiplied by the scale of velocity divided by AB length. So it is shown here the magnitude of the velocity of the angular velocity of AB is 5.66 radian per second. So this is the velocity polygon. To draw the acceleration polygon, you have to make this table. The table consists the first column length, second column is length in meter, third column is velocity in meter per second. For all links, the acceleration radial component column and acceleration tangential component column. So write all the linkages of your mechanism. First link is OA. We have written that OA in the first column, then AB, then slider B. The lengths are known. Length of OA is 0.15 meter. Length of AB is 0.6. Slider don't have the length, so we put the dash here. The velocity of OA is already calculated 4.71 meter per second. Velocity of AB is 3.4, which got from the velocity polygon. Velocity of slider is 2.9 we got it from the velocity polygon. Now, any mechanism, all the linkages of mechanism will have two components of acceleration. First one is the radial, or it is also called as centripetal. And second one is the tangential component. The radial component or centripetal component is given by velocity square divided by radius of that link. And tangential component is given by alpha, angular acceleration multiplied by radius of that link. That is already written in the table. So here you can see this is the radial component and this is the tangential component. So remember this, for first link, that is the crank, if crank is rotating with the constant speed or uniform speed, then it will have only one component of acceleration. And that is the radial component. If it is not rotating with uniform speed, then that crank will have two components, radial as well as tangential component. Remember this. And slider will have only one component, that is the line drawn parallel to the line of Prokop of slider. This you have to remember for all numericals. So where to begin after completing this table of acceleration polygon? You have to select one appropriate scale. Here in this case, we have taken the 1 centimeter to 20 meter per second square. Now, where to start the acceleration diagram? As usual, you have to locate the pole. So we have located the pole. Remember that for acceleration diagram, we have to show the letters with the dash. So O dash, pole is the fixed position from your space diagram. So we have located the O dash with one single point. After locating that O dash, you have to draw the acceleration of AO link. This is the AO link. The acceleration for OA link is only one component of acceleration, that is the radial or centripetal. The radial component, you have to fix the direction of that radial component. To fix the direction of radial component, you must know the center. So for OA, the center is O. Fixed point is always center for any link. So O is the fix. So radial component is moving toward the that center. So means radial component is in going in the downward direction. And this downward direction vector, you have to draw a line parallel to this link AO in the downward direction. From where either O or A point should be available here. So O dash is available, means you have to draw a vector parallel to OA link in downward direction, which is parallel to the AO. So this is the vector OA, acceleration of O dash, A dash. It is the parallel line to the AO in downward direction. After drawing that, next link is AB link. This AB link will have two components. One is radial and second one is the tangential. So radial component of AB will be acting toward the center. Center is A. Always remember center for if both points are moving, A is moving, also B is also moving point of link AB. So let's consider this AB link here. Both points are moving. The center will be the A. So radial component will act toward the center, means radial component will go in this direction for AB link, right? So remember this. So we are going to draw a radial component of AB, which is a line parallel to the AB link in this direction. From where you have to draw, either A or B dash should be available. So we are having A dash. We have to draw one parallel line to the AB in this direction from the A dash. So this is the radial component of AB, which is the parallel line to the AB in the right upward direction. So what magnitude? The magnitude of radial component of AB is here, 19.26. By scale, you have to draw this by using the scale. So radial component of AB is drawn in this direction. Then this AB will have another component of acceleration, and that is the tangential component to AB link. Now this, where the radial ends at x dash, from there you have to draw the tangential component, a perpendicular vector. So this is the tangential component of AB. Now we don't know the magnitude of tangential component of AB, just you have to draw a perpendicular line to the AB. So this is the tangential component. After drawing this tangential component of AB, then comes the link B, means a slider. Slider acceleration is a line drawn parallel with the line of torque of slider. So line of torque of slider is horizontal. Draw one line from the O dash that will cut this perpendicular component, and this will be the acceleration of slider B, right? So before, you can see how it comes. This is the acceleration of B, and where this tangential component slider vector cuts, that is the B dash. So this is the B dash point. After getting this B dash point, B is located. Now you have to check where the radial component of BB start here, where the tangential component ends here. So you have to draw one line here, which gives the net resultant acceleration of AB. So see here, this is the resultant acceleration of AB. Now our acceleration diagram is completed, but we have to locate the M point. How to locate the M point? To locate the M point, which is the midpoint of link AB. Now where is the AB vector? This is the AB vector. This line is the AB vector. Obviously the M point will get located on the AB vector only. Where it will cut? In the same position where it is in the space diagram or same ratio. So how you have to locate? To locate this, you have to take again A dash M dash divided by small a dash B dash equal to capital AM divided by capital AB. This is known to you, this is known to you. A dash B dash, you have to measure this vector here. After measuring that, you have to keep here. You will get the A dash M dash in centimeter. After getting that, you have to see here. That calculation is shown here. You will get the A dash M dash 2.5. So you have to locate the M point at 2.5 from A, right? Then join the O dash M dash. And this gives the acceleration of M. Now how to find out the acceleration of M? To find the acceleration of M, you have to measure this O dash M dash distance. See here. We have measured the O dash M dash, multiply it with the acceleration scale. Whatever the value you are getting, that is the acceleration of midpoint of the connecting rod. That is 115 meter per second square. Now to find out the angular acceleration alpha of AB, you have to measure the vector x dash b dash. X dash b dash is your tangential component of AB. So tangential component of AB will be given by x dash b dash measurement multiplied by scale. So you will get 80 AB from here, right, in meter per second square. Now by using your equation 80 AB equal to alpha AB multiplied by length AB, you can find out alpha AB. Because AB already calculated, AB length is known for AB, you will get the alpha AB. See here, the calculation is shown here. So it is 163.33 radian per second square. In this way, this numerical completes here. So this is the total numerical where we have seen how to draw the velocity